This is the first lecture on flip-flops, and we're going to start with an RS flip-flop, which is the most primitive of flip-flops. This was the original flip-flop that has some drawbacks that we'll talk about. And then there are more sophisticated flip-flops that we'll get to that get around the drawbacks of the RS flip-flop. But an RS flip-flop, as well as other flip-flops, they have the ability to store data, and we'll talk about exactly what that means coming up. But to start with, here is the circuit symbol for an RS flip-flop. It's just a box. Over here are the inputs, and it gets its name from these inputs here. One is the S input, the other is the R input, and then over on this side, Q and not Q, those are outputs. And it's pretty standard that flip-flops, all flip-flops, whether it's an RS flip-flop or some other type of flip-flop, the outputs are usually labeled Q and not Q. Now this is one way to make an RS flip-flop, is you can take two NAND gates and connect it up in this fashion. This is called a cross-couple connection, where the output of one NAND gate goes to, or is connected to, one of the inputs of the other NAND gate. And you can see that the output of this one is also connected to the other NAND gate's input. So all RS flip-flops have these gates that are cross-coupled. Now if you look in the book, you'll see that in the book they have an RS flip-flop that's made out of cross-coupled NORs. And before the end of this lecture, I'll show you another RS flip-flop that's very similar to this one, just modified a little bit. So it's important to understand, from the start, that this isn't the only logic circuitry that will give you an RS flip-flop. There's other logic circuitry. Okay, but the common concepts that we'll get to involving an RS flip-flop are true no matter what the logic circuit. And this truth table shows how this RS flip-flop functions. So first of all, notice that when both inputs are 0, both outputs are 1. When we have a 0, 1 at the input, Q is 1, not Q is 0. When S is 1, R is 0, you got Q equal to 0, not Q equal to 1. And then when both inputs are 1, you can see in the truth table we have these X's. And up to this point, we haven't seen this type of symbology in a truth table. Well, what the X's here mean is no change. Okay. All right. Well, let's go over some terminology here. And the first that we'll start with is this second row. When S is 0 and R is 1, which makes the Q output 1 and the not Q output 0, this is called the set condition. Okay, we say that the RS flip-flop is set when we have this second row here. Now, it's important to understand that what set refers to is the value of the outputs. So it's the fact that Q is 1 and not Q is 0 that we say that the flip-flop is set. It doesn't have anything to do with the inputs. It just so happens for this particular RS flip-flop, in order to get this set output, S has to be 0 and R has to be 1. But by the end of this video, I'll show you a different RS flip-flop where the set condition happens for a different set of inputs. Okay, so set refers to Q equal to 1 and not Q equal to 0. Very similarly, when Q is 0 and not Q is 1, that's called the reset condition. Okay, we say that the flip-flop is reset. And again, it has to do with the value of the outputs. Okay, for this particular RS flip-flop, to get the reset condition, you need S equal to 1 and R equal to 0. Okay? Alright, the next row we're going to look at is this top row, where both inputs are 0 and both outputs are 1. And you see this is not a typo. You see, you may think it's a typo because, as you learned in Boolean algebra, when you put a bar over a variable, that means not that variable, that means opposite of. So you see, based on our definition of what not a variable means, well, if Q is 1, not Q should be 0. But you see, this logic circuitry does not yield that. When these two inputs are 0, both outputs are going to be 1. So because this goes against our definition of what not a variable means, we call this the ambiguous state. And you see, this is one of the drawbacks of the RS flip-flop, is that it has this ambiguous state in its truth table. And normally you want to avoid this state. Okay, you never want to allow both these outputs to be 1 because it goes against the definition of what not a variable means. So to avoid it, you just never let the inputs both equal 0 at the same time. Alright, well, I saved the bottom row here for last because this is why this circuit exists, because when both inputs become 1, the outputs don't change. And this is the storage state. This is when the flip-flop is storing data. Okay, and that's its purpose. Okay, because if I have some change in input and yet the output remains the same, that indicates that the data, the zeros and ones at the output, represent past values, right? Because by the very nature of an input changing, time must have passed. And if the outputs remain the same for that time lapse, right, that time that has passed, well, that means I'm retaining information. I'm retaining or remembering information from a previous time, and that's what storage of data is. Okay, storage of data is when your output or outputs remain the same for some given change of input. Okay, we'll talk much more about this in the next video also, because in the next video we'll go through and we'll prove some of these rows that are in this truth table. Okay, but the last thing in this video I want to show you is I want to show you a slightly modified RS flip-flop from the one we just looked at. Okay, see, here's an RS flip-flop where you've got the cross-coupled NANDs, but also, in addition to the cross-coupled NANDs, you have some inverters at the input here. See, an inverter for S, inverter for R. And you see what happens is that your truth table gets flipped. That rows 1 and 4 get flipped. So you see now your ambiguous state is down in the last row and your storage state is up in the top row. And then also your set and reset conditions get flipped, rows 2 and 3. So you see both of these circuits, whether it's just the cross-coupled NANDs or the cross-coupled NANDs along with the inverters, they're both RS flip-flops. They both have ambiguous states, storage states, set condition, reset condition. It's just that they're in different parts of the truth table. Okay, so that's what I meant by what I said earlier, that even though the logic circuitry can be different depending on what particular RS flip-flop you have, what's always the same no matter what the logic circuit of the RS flip-flop is that you have those 4 states: storage, ambiguous, set, and reset. Okay, the next video, as I mentioned, we'll go through and prove some of the rows of this truth table, and then also in a future video we'll look at an RS flip-flop being used in a home alarm system, a very primitive home alarm system.